the reverse engineering one. We're going to get started with a couple announcements.
You're not sharing screen.
Oh yeah, let's share screens. It comes. Okay. Great. We'll just leave that up there for now.
Here, Nick. Here is your mic.
Sure. This shows where you can hide this. It's all right, we'll just leave it there for now, I guess. Sorry guys, this is annoying. Okay. You guys ready to get started? Let's get started. So we're gonna get started with a couple announcements. So as you guys know, the server is currently down. That server includes like the challenges, like for example, our web and our phone challenges, as well as our auth bot. So if you're in our Discord server and you do not have a UIUC role, just let us know. We'll get that sorted. Yeah, so our server is down right now, which includes like the auth bot, which gives like the role to Discord. So if you don't have a UIUC role in Discord, just let us know and we'll get you on. Congratulations to everybody that played O2F this past week. Everybody that played placed third, and we won $100 as a club. So great job with that. Next up is fall recruitment. So we need challenges. If you guys are interested in writing challenges, the fall recruitment event will be like a CTF, and it will be just in-house. We'll have pizza and everything, so I'm looking forward to it. If you guys are interested in writing challenges, just reach out to us. A challenge, for example, are the things that you're going to see after this meeting today to solve, and the other web challenges and things like that that we've put on in the past. Just let us know.
We're doing it's like three challenges for each category. So we're probably gonna need like 6 to 8 more challenges. So if you're interested, you get a free dinner out of it. So I'll pay for your dinner. So,
excellent. Yeah, Thomas, you want to take the last one?
Sure. So thanks to Sandia National Labs, a few of us are going to Purdue from October 16th to 17th. That will be, so we'll be leaving Friday and we'll get back Sunday after the Sunday, October 17th meeting. So we are going to need a presenter for the Cone 2 meeting. If that's something you're interested in, and if you're experienced a little bit past Cone and would want to teach that, then feel free to reach out to us. Otherwise, we're probably going to reach out to you. You know who you are.
Okay, let's get started with today's meeting then. So we have the meeting flag for today, along with some great reversing memes and I guess just CS in general. So go to ctf.sigpwny.com and type in this meeting flag for reverse engineering 1. So if you're just new with us today, again, the link is ctf.sigpwny.com. You'll create an account with your school email and then submit this text to get 50 points for today towards your scoreboard. Don't worry, these slides will be posted. Chris, would you mind exporting these as a PDF and then uploading them? Thanks so much. Yeah, so I'm gonna give you guys just about 10 seconds to take this down and type it in. And in the meantime, I'm going to explain the memes to you guys. So a lot about reversing is going to have to understand some of the low-level aspects of computer systems, including pointers. And so can I get a raise of hands if you have taken CS 241 or like an ECE equivalent? Okay, good. So you guys are familiar with pointers. We're gonna get to them more, but a pointer is basically basically a memory address. And that when we navigate to that memory address, it contains an integer in this case. It's an integer pointer. And of course, it can also contain pointers. So we have people pointing to the integer, which is funny. This meme on the left, we have a complicated piece of code and the compiler can compile that down to one instruction, which is fascinating from a compiler perspective and very scary from a reverse engineering perspective. Okay, let's move on. So today's meeting is about reverse engineering. We're going to start with a brief overview about what is reverse engineering, as well as what happens during the compilation step and what the compilation step produces. And that's what we're going to be working with. We're going to use 2 tools today, the first of which is Ghidra. So I encourage you guys to all download that right now. Check out the Discord announcements and get that downloaded. If you're unable to download it, don't worry, raise your hand. We're going to come around and help you guys download that so we can do a walkthrough today together. And then GDB. If you're on Linux, you've already probably got it. Check the Discord announcement for instructions how to install that. Okay, so let's get started. So what is reverse engineering? Reverse engineering in a broad sense, well, at least as broad as computer science gets, is that given a program, figure out what it does and how it works. And so this almost seems trivial, right? If I give you a piece of C or C++ code, you can be like, yeah, that's a for loop. It's going to add up some numbers and return the sum. But that's often not, it's not so simple when we just get the program in its compiled form. And we're going to get to that in a bit. Let's look at some applications of it. So let's first focus on some unethical applications. So therefore, we should not do these. First of which, can we crack programs? Can we produce keygens, which is like a key generator, right? So for example, how does Microsoft Word validate that a product key is the correct key, right? Somehow there's some logic going on. At least this used to be how it was till now they have online authenticator stuff. But can we reverse that process in order to produce a key which can work, right? Reverse engineering. How about this? In a compiled program like Rocket League, there is decryption keys for in-game assets. So Rocket League encrypts its assets. So it encrypts its 3D models. So it's not trivial for me to just take that, put it into Blender and produce a nice render. Instead, we have to actually reverse engineer the game, understand the file format, understand how it decrypts that file format in order to reverse that to produce the assets which I can now use in my renders. Probably the most important part about reverse engineering is, given an application, can we find a bug in the logic, right? So this is going to be a gateway to next week about how can we, when we find a bug in the logic, how can we exploit that to take control of the computer? But the first step is always reverse engineering, understand how the program works and the logic behind it. At the end of the day, programs are written in many different languages. A lot of us are familiar with C and C++. That's what we're going to be working on today. Java is another example. Python is another example. And all the millions of other languages which exist and have different compilation processes, they produce different kinds of executables, which may or may not require different strategies. Today, we're going to be focusing strictly on C and C++ compiled programs for Linux. And so if you're on Windows, we need to have a Windows subsystem for Linux. If you're on Linux, you're already good. If you're on Mac, you're going to need an Ubuntu VM. Okay, let's move on.
Real quick.
Yeah.
If you're interested in Windows, we're going to do 2 Windows meetings later this semester, actually. So it's the first time we're ever going to do Windows meetings. So if you're interested, stick around.
Okay, awesome. And I want to really focus today on getting you guys hands-on experience. So I'm going to keep this meeting to about 20 minutes, hopefully. Always goes longer, but then we're going to be helpful and we're going to walk around and we're going to make sure that everyone can solve the first challenge at least. Because understand that reverse engineering is going to be the most difficult thing that we've covered so far in this semester. And so I really want you to have that knowledge going into it. So I encourage you all to pay close attention and just practice, practice, practice. So the first step to understand is the compilation step. When I have C and C++ source, I can't execute that, right? Computers don't understand the ASCII text that I've typed, and they can't understand that in order to execute it. What needs to happen first is that we send that C and C++ code through a compiler. That compilers will take the source code and produce machine code. This machine code is then packed into what we consider an executable, which on Windows, you may be familiar with .exe files. That's an executable, which came from a C and C++ source file, right? Or a combination of them. On Linux, that's probably a file without an extension that you can execute. Like I have a screenshot here of me executing a compiled program, and that's executed like /. My program will execute it, and in this case, I have a hello world program, right? And so the first thing to note about this, I think I'm on the next slide. Sure. Is that this executable contains machine code, and this machine code is dependent on the system architecture which we're running. So all of our laptops, okay, not all of them, now this is different, right? Most of our laptops, I'm looking around, I see a lot of like Linux, Windows-based machines, well, right, so it's a reasonably good guess to assume that you're using x86, probably a 64-bit version of it. I see a Macs out here, so it could be different, right? We have the new M1 chips things.
Does anyone have the new M1 chip? Just raise your hand.
Okay, so you threw off my generalization, thanks a lot.
So it'll be a little bit different. But if you run inside like a virtual machine, which for those two, I'll help them.
That's okay. Ghidra will still work the same.
Oh, does it?
But you'll have to use an Ubuntu virtual machine. Actually, you'd have to emulate
They
x86.
can't,
Yeah.
because
We'll
they-
get to it.
Yeah, we'll deal with it. We'll deal with it.
So anyway, when I compile it, I have to choose at compile time. Which am I going to target? Am I going to target my computer, which has x86, or will I target another person's computer with a different architecture? Right? Will I target the router or a game console which runs MIPS or LC3 for people who are experienced with it from ECE perspective, right? Ultimately, it's what your processor understands, and the processor understands these machine codes. but it does not understand C and C++, right? So that's why the compilation step is necessary. Unfortunately for us, humans have a very hard time understanding assembly. So the idea then is, given this executable, given these hard to understand assembly instructions, how do we reverse engineer back to the original C, C++ code? So give you a little bit more background. So it's going to get into technical specifics about x86, how this all works out. Is that x86 uses many registers and a stack, and it uses a lot of other things, but I'm going to focus on these two things right now. Register, consider this a variable like x, y, z, right? And I can say that x equals 5, and I can say that y equals 7. I can later change my mind and say now x equals 10 and y equals 5, and I can say x plus y and these sorts of things, right? And so we have a bunch of registers of general purpose variables which we can use in our assembly. And then the stack is useful for pushing and popping, especially for function calls. We can save registers on the stack. We can push and pop data on the stack. And you'll see these make an appearance in our next example slide. Okay, so let's look at this process, right? When we compile something, what really happens? Here we have our C code on the left. Let's quickly observe what it does. So this is going to compute 1 plus 2 plus 3 plus 4 plus 5 all the way up till n. So if I say n equals 10, it'll compute that plus 8 plus 9 plus 10, right? And it will return whatever that result is. And so here's what the compiler produces. That is what the processor understands, right? And it is non-trivial to go from the right to the left, right? That's the hard part. That's reverse engineering. It's us looking at the right side and trying to infer its left side behavior. So let's break it down. I've copied this excerpt on this whiteboard so I can annotate it. Everything I've written in red are those registers which I told you about, right? General purpose variables which we can read and write to. So the first thing to note is that in this particular architecture, I'm going to go through this example, but I will warn you that we don't actually have to pay attention to these close details all the time. So I'm going to do it just so that we can get some experience of what you can expect when you open Ghidra. EDI, at the beginning of a function, this is the first parameter. So this is n. For the duration of the program, let's consider EDI equals n now. So the first thing it's going to do is say, let's test EDI against itself. And the test instruction computes the bitwise and. Ooh, yeah, how do I draw an ampersand? Yeah,
I can do it. I'm really good at it. I'm really good at it.
Later, promise, later. Thank you. I'm just going to say and because I really can't draw that. It's going to notice that EDI and EDI will yield a non-zero value if EDI is non-zero. We'll yield a 0 value if EDI is 0, right? And then to say jump if equals means that if it's 0, go to L4. And these green, what we call labels. And so it's like targets where we can jump to. So in other words, this block here checks, is n 0? If n is 0, go to here. This says move n, which is 0, into edx, which is a new register, right? So it's like x equals y, this is a simple variable. Go to L2, here we are. Move n, which is still 0, into the return value. So when we say EAX, this is our return value. And then when we ret, it returns 0, right? So that was a complicated experience just to say that if n equals 0, return 0, right? So it's non-trivial to go about this way. Let's look in the general case. So if it's not 0, it will just continue to the next line. So now we're going to say that our general purpose EAX equals 1. We're going to say another variable EDX equals 0. So just consider this like x and y, right? These are just fancy names for variables, EAX and EDX. And then here we're going to start a label. We're going to say add the two together and store the result in EDX. Right? That's how we can interpret this instruction. So first step is going to be 1 plus 0, store it in EDX. So now EAX equals 1, EDX equals 1. And then we're going to increment EAX. So now EAX equals 2. And we're going to compare n against our current iterator value. So after we looked at this for a while and stared at it, we observed that EAX, that's actually I, right? So in our code, we're going to say I equals 1, right? And we're going to increment I every time. And we're going to add I to our result, right? So we observe that EDX is our result. Right, so now you can start to get that map of what's going on here. And we're going to loop until EDI is not bigger than EAX, right? And that's going to occur when EAX is greater than EDI. Is that right? Yeah. And so that's while I is less than or equal to n equivalently, right? And then finally, we're going to move that result, remember edx equals result, into the return value and return, right? So that is a high level overview about what assembly is and how it does, or how it works. I don't expect you guys to have understood that in its entirety, and I don't expect you to master that. In order to master like reading assembly like this, it's necessary for you to get hands-on practice, which we'll do today. Yes?
So that's a general, like an accurate, like x86, I think it's x86 something.
Yes, yeah, exactly. This is x86 assembly. Good question. In fact, there's a one-to-one mapping between x86 assembly and bytes. And so the processor operates on a series of bytes, right? And the disassembler can take the bytes and produce this, what we call disassembly, which is the assembly, right? That we're looking at, the bytes that it corresponds to. And the next step is to take a decompilation, which is the C code, which we've originally written to, right, from the disassembly. So again, I don't expect you guys to have mastered that, or even to be probably difficult to understand. I expect you guys to learn mostly from hands-on experience today, using the challenges we got as we walk around. But any questions on that before I continue? I know that's a lot. Just take note that we have registers, right? And we have labels. And the label is just a fancy name for where to jump to. And when I say jump, I just mean change where we're currently executing, right? Okay, we're gonna continue. Next slide, Thomas. Thank you. Okay, yeah, so if you didn't like that, I didn't like that either, right? I don't like looking at assembly. I'd rather look at C. And so that's where Ghidra comes to the rescue. So Ghidra is an open source decompiler and disassembler. What it's able to do is transform the executable to a disassembly. And it's also able to translate disassembly to a decompilation of what it thinks could be the original C code. You'll quickly learn that that is not a perfect process. Sometimes looking at the C is just as ugly as looking at the assembly, but it's super helpful. It was in fact written by the NSA. Yeah, exactly. Okay, next slide. So this is what Ghidra produces when we're looking at the same binary. So even though it's not the same, so it accomplishes the same result, right? But it's not the same source that I gave it. Ghidra is doing its best guess as to, given the disassembly, what the original C looks like, right? So it did what we just did, but automatically, right? So even though this is still kind of complicated, it's way more complicated than looking at the left side. It's much more digestible than looking at the raw assembly, right? And a lot of times a good way to learn assembly is to look at the disassembly and a decompilation or the original source side by side and see how it all interacts. Do note that I did rename some of these variables here. A lot of times you do get the symbols of the function names. You do not get the symbols or the names of the local variables. So you kind of infer what they do, and then you can rename them, and then it gives you clues about other names, and you can rename them. That's the process of reverse engineering. Okay, next slide. Okay, let's do it. So next up is a demo for Ghidra. So everybody open Ghidra. If you can't open Ghidra, don't worry. I'm going to do my best to present it here. Okay, so the first thing I'm going to do is open Ghidra, and I'm also going to download the Hello World from C.
Who wants to open it? Raise your hand. Or watch.
Okay, so everybody download the first RE app. Feel free to follow along. Otherwise, I'll just do it and everybody can watch. When you open Ghidra, you'll see something that looks like this, where you see no active project. So I hope everybody's on that screen. What we're going to do is create a project. And so I might call this, it's going to be we're going to click through a lot of default prompts. Every prompt that comes up, we're going to click the default value. So here I'm just going to click next. Project name, I'm going to call SIGPwny. I'm going to call it SIGPwny demo because I already have a repo named SIGPwny. Finish. Okay. Finally, the next thing I'm going to do is drag and drop the. Then what you do is download the executable you're trying to reverse here. It's going to import it, and we're going to click through all the default element options again. It's going to do its thing. Finally, I'm going to double click it to launch the disassembler and decompiler. It's opening it on my other screen. Okay, and then this is the view which you see once you're in the file. A lot of crazy stuff going on. We're going to ignore a lot of noise. It's a lot of noise here. We can ignore most of it. Can I get a show of hands who is currently open to Ghidra though? Excellent. Yeah. Okay. Good, that's good. I encourage you guys after this to help your neighbor if they haven't been able to open it yet. Okay. All right, we're gonna move on. So the next thing to do is expand the functions.
Give everyone a minute. They're still trying to open it.
Good, because I can't expand functions for some reason. Oh, good. I think that one. Okay, I'm gonna walk around real quick just to help people install it. Okay, how are we looking? How are we looking?
No, it should be there, but no, you know what's worked or not.
All right, does anyone in Zoom have any questions? That's a lot of questions. For the home directory for JDK, I would recommend reinstalling the latest version of JDK. Additionally, make sure you're downloading the release build and not source, because sometimes you won't find the Ghidra run.bat.
Okay, I'm gonna move on so we have time to do the challenges. I'm extremely happy that I've never seen so much Ghidra in one place. So I'm very happy about that. Let's move on. First thing to do is click yes to analyze. Remember, we're going to go through. Oh no. What happened? My laptop's frozen. That's not good. It's fine. Yeah, go for it. What happened?
All right, Nate is going through technical difficulties, so we are going to pivot to my computer. Run. Yep. Because that would have been a problem. First RE. I already got it. I already got it, Nate. You sure? All right. All right, I'm gonna pause the recording. Okay, hello, we are back Zoom. Making you co-host, pinning you.
Okay, we're back online. Yeah. Let's go.
All right. Make sure you walk over there.
Okay, sorry everybody, I'm back online now. My computer happened to freeze. So here we are again. Maybe the NSA hacked me, who knows? No, I'm joking. But anyway, just step through all the default options. So like press OK, then press analyze, then press whatever is the default option. And you should arrive at this screen. The next thing to do is what we should always do is look for the main function first. And to do that, we're going to expand the functions here. And we see a lot of functions which we're not interested in. But if you scroll down, you can see the main function. Let's go ahead and click the main function. And then from here, on the left side, you can see the disassembly, right? So this is what we talked about earlier. You can see the RBP, RSI, EDI. These are the registers, right? And we can see we're doing stack stuff, and we can see all that. But we can also see on the right side the decompilation. And we also observe that the decompilation is not perfect, not by any means. And we still have to read through a lot of gibberish just to try to understand the intended functionality of this program. But the good news is that it gives us a lot of hints, right? We can see printf, please enter the flag. So we know that it's going to print, please enter the flag, right? And in fact, we already see the flag right here. We see that the flag is SIGPwny hello Ghidra. And then what we do is we observe, if we were to reverse this, we realize that that's just checking if every character in the string is the same, right? So I'll leave that to you to step through. This is actually stir compare, but it was compiled and optimized to this inline functionality by GCC. And then we observed that if it was in fact every character is the same in your input and SIGPwny hello Ghidra, then it's going to print flag is correct. And from here we can literally stop because we already have the flag, right? And so from here, go ahead and submit that on the CTF. So I also want to show this to you, everybody. Can I have your attention for just a sec, guys?
Hey, real quick, up front, Nate's got some cool stuff.
So after you download this file, if you're on Linux or on Windows WSL2, right, the first thing to do is we want to execute it to see how this works, right? After we know the flag already, so we already know the answer. And to do that, we have to do first RE like this. But we observe that it's permission denied, and it's necessary that we all do this. chmod +x first RE. So I have these instructions. What this does is actually tells, please don't freeze.
Did it freeze? Do we want to start working on that?
Yeah.
Okay.
Okay.
I got it.
We're gonna froze again, but that's what you execute, and then you can execute it using /.
You do want to explain that while I set up?
It's been explained, I think. You just
All right.
open the slides. We get it.
Yep. Okay, and we are back.
Let's go to the next slide.
Next slide.
Okay, I'm about to finish up this up. I just have a couple more notes. Is that what we're doing right now is called static analysis. So when we're looking at the binary in Ghidra, we're looking at the instructions and we're staring at the decompilation and we're trying to wrap our human minds about what is going on. That's static analysis. Another useful thing for reverse engineering is called dynamic analysis. It's basically just debugging, right? And so some of you may be familiar with GDB, some not. GDB is a debugger. And what this allows us to do is step through the instructions as it's executing them. And we can observe, for example, in this code, when I'm right here, what is the value of EDX? I can literally say to GDB, print EDX. And this will also help me wrap my mind around what this algorithm is actually doing, right? So you can show the registers, which we talked about. You can show what's on top of the stack. You can show what's in the other memory regions, what are the constants. I can set a breakpoint. That's how debugging works. I can set a breakpoint on a certain function which I'm interested in. And I can try and input. I can redo things. And so that's the dynamic analysis. There's a challenge today, which is very helpful if you use dynamic analysis. But you can solve it if you're exceptionally good at it. All of these things take so much time to get used to. So I implore that you just have to keep practicing and don't let it discourage you. Ask for help. We're here to help you. I want to see everybody solve the first challenge, get Ghidra running. And the next thing, so I was going to do a GDB demo for you guys, but unfortunately,
No promises.
unfortunately, we're not going to be able to do that today with my laptop freezing up. But something I'll come back to maybe this Sunday here. So I've got these two awesome slides for you guys. I have a Ghidra cheat sheet, and then the next slide is a GDB cheat sheet. And so I'm going to post these in the Discord channel. Some of the most critical things for Ghidra is the ability in the decompilation to rename variables. So as you saw in the Ghidra decompilation, as you see now, those variables are UR1, UR2, not useful names. You can click them and press L, and you can rename them to odd and like result and things like that, input. Control L gives you the ability to retype the variable. So if it's interpreted as an integer, but it's actually a character pointer, retyping the variable helps the decompiler yield more interesting and useful decompilation results, more accurate. Type semicolon to add comments. All of these things are very useful. I'm going to throw these up. I'm not going to read through all of them here. GDB is likewise.
There we go.
I'm just going to throw these up. Feel free to look at these when you're there. So that's all I've got for today. I've got, I think, 4 or 5 challenges for week 1 reversing. The first 3, I encourage you to, if you guys are able to solve the first one, let's all take a look at ROT 13. Help your neighbor get to know the person sitting next to you. See if you guys can solve it together. Start with RD intro if you haven't solved it. All these can be solved with Ghidra today. With the exception of the debugger, you can solve with Ghidra, but it's highly encouraged to use a debugger. We have it. I didn't really think about how to use GDB. Of course, my laptop's broke. Come this Sunday, and I'll help you out with that. But practice, practice, practice. The only way that you can possibly get good at reversing and understanding assembly is by looking at assembly. So that's all I got for you guys today. I'm going to come around and help. We got a lot of good people helping. Raise your hand if you need help. Talk to the person next to you. See if you can solve all the challenges together. Okay.
Thank you, Nate. This was awesome presentation.
Yeah. Oh, last thing. Next week. So if you guys like what we did today, and you're very interested in how we do more advanced things, I've got very cool stuff coming up. This next Sunday, we're going to do reverse engineering 2, right? So I hope you get all the practice you can. You may have to work outside of just what we do here. But I'm going to do symbolic execution. We're going to do side channel analysis. We're going to do self-modifying code and some VM obfuscation. So very cool stuff. And then next Thursday, we're going to do instruction components. So that's all. Thank you guys so much.
All right, and thank you, Nate. This was awesome. I just want to say I've never seen this many people actually using Ghidra in a room. Usually, whenever we try and run a RE meeting or like one of those things, it falls apart. Also, Ghidra wasn't out in 2019, I don't think. Like, what?
It's recent. It's pretty recent.
It was really new. So like, this is the first meeting we've run where like people know Ghidra. So like, this is awesome. A few super quick announcements. Specification on the fall recruitment event. The actual event itself is going to be on October 23rd. So that's a Saturday from 12 p.m. to 6 p.m. There will be food provided and there will be recruiters there. So a little bit more info there. That is all from me. Just wanted to specify that. All right, I'm going to end.
Let's solve some challenges. Let's go.
I'm going to end the recording. Make sure to like and subscribe. All right, bye.